In this demo, we're going to add a scoring module to a Microsoft Machine Learning Studio ML Designer pipeline. We'll see how the module attaches to a pipeline and why it attaches that way. We'll also talk about how a scoring module is generally used and what it's for. Now, before we begin, there are a few assumptions this demo makes. First, to access the Microsoft Machine Learning Studio ML Designer, you'll naturally need a Microsoft Azure account. If you don't have one, you can get one for free at azure.microsoft.com/free. With an account, there's also an assumption that you've created the necessary machine learning resources and know some basics with regards to navigating your way around the ML Designer. Okay, now with that settled, let's go ahead and navigate to the Azure Machine Learning Studio in our browser. So what we want to do in this demo is add a model scoring module to an existing pipeline. To do that, we need to go to the ML Designer. So let's go ahead and click on the Designer option in the left-hand menu. Now, in the interest of time, I've created a few pipelines ahead of time. I've named them based on their purpose. I have a pipeline for training a regression model, a pipeline for training a classification model, and a pipeline for training a clustering model. For this demo, I'll choose my regression model, as it'll be the easiest to walk through and explain. So let's go ahead and click on it. Good, now we're presented with the ML Designer. On the canvas, I've already got a set of modules. Now before we set to work on adding a scoring module, it's worth a quick overview of what this pipeline does. The purpose of this pipeline is to create a model that accurately predicts the price of what a car should be based on a number of variables. The future of this pipeline would ideally be to generate a model that can be used by external sources to accurately provide appropriate prices for cars. Now at the very top of the canvas, I have a dataset. There's a sample dataset from Microsoft that represents information about cars. There's all sorts of information about cars in that dataset. Things like horsepower, mechanical specifications, miles per gallon, and so on. Importantly, it also includes information about what the price of each car is. After the dataset, there's a few modules that transform the dataset. I won't go into too much detail about that in this demo, but these transformers augment the dataset by removing undesired data and reducing bias on some of the remaining data values. Then, after the transformation of the dataset flows through a split data module. Now this module takes 70% of the data from my dataset and sends it over to a train model module, and that's where the bulk of the magic in this pipeline happens. The train model module uses a linear regression algorithm to walk through 70% of the values from my dataset, chosen at random, and the purpose of the train model module is to evaluate the dataset that it's given to try to create an algorithm that can accurately predict what the price of a car should be. But how do we know that the algorithm that the model training comes up with is any good? Well, that's where the model scoring module comes in. The purpose of the model scoring module is to compare the model's predictions to an actual dataset. To make that more clear, let's add the scoring module to this pipeline. First, let's expand the Model Scoring and Evaluation section of the Asset Library on the left side of the canvas. Now let's find the Score Model module and drag it onto the canvas below the Train Model module, but slightly to the right. Placement doesn't actually matter, but it'll read a lot easier if you can place it like I said. Good. Now let's connect the output of the Train Model module to the left input of the Score Model module. The left input of the Score Model module is the input used for models. Okay, now before we proceed, let's quickly talk about the Split Data module. The purpose of the Split Data module is to take a dataset as an input and split it into two sub-datasets. There are a few ways that the data can be split. Now in my case, I've opted to randomly split the data into a 70-30 split. I have no way of knowing which data will be in which dataset because the module randomly selects which data will go into which output. And that's the key point. you'll notice that the split data module has two outputs. The output on the left contains the 70% dataset, and the output on the right contains the remaining 30%. The bulk of the dataset is sent to the model trainer for, well, training. Now we're going to use the rest of the dataset for scoring. So let's connect the right output of the split data module to the right input of the score model module. The right input of the score model module is used for datasets. Alright, so now we have a scoring module connected to our model training and a dataset. So now let me explain what this is going to do for us. As I said, the split data module splits up the dataset and feeds 70% of the data into the model training module, and then feeds the remaining 30% into the scoring module. Now the scoring module is connected to the model trainer. What this all means is that the model scoring module is going to apply the trained model to the remaining 30% of the original dataset. If the model is trained well enough, we should see its predictions reasonably close to the actual data in the dataset. And there's actually a couple things worth noting here. First, the predictions may end up looking like they're all over the map. That doesn't actually mean that the model is bad. Well, of course, it could mean that the model is bad, but it could also mean that the data is bad. For example, we know intuitively that there are cars out there that you would pay quite a lot of money for just because of the brand name. It doesn't mean that the cars are actually better or even worth that price, right? And next, despite the naming of the module, the score model module doesn't actually score the model per se. Rather, it gives you some information from which you can determine for yourself if you think the model is good enough. AI is never going to give you absolute answers, only probabilities. Based on some input information, the probable answer is XYZ. In fact, there are plenty of times where you can feed in exactly the same information into a model trainer and get back slightly different answers. Regardless, in my opinion, it's a really good idea to use the model scoring module to compare the results of the model that you're training against known data. When we train a model to make predictions, we obviously want to know if our model is any good. Now, clearly we can look at the model predictions and compare them to actuals and gauge it visually, but that only goes so far. After all, eyeballing data like that is pretty subjective. Worse, imagine if you had millions of values. The best models are trained with as much data as you can give it, but you're certainly not going to want to eyeball every single value that comes through, right? Well, that's where model evaluation metrics come in. Using certain metrics, we can compare all of the predicted values against all of the actual values and make a determination as to how good our model is at making predictions. So let's go over a few of those metrics now. First up is the mean absolute error metric. This metric describes the average difference between the predicted values and the true values. Sometimes the true values are referred to as actual values. So imagine that I have a model that predicts the price that a car will be. So imagine I have an actual value of $1,000 and a predicted value of $1,200. In that case, the mean absolute error would be $200. In fact, if my actual was $1,000 and my predicted value was $800, the mean absolute error would still be $200 because this metric is based on absolute values. Then what this metric does is take the average error value across all the predictions and actuals. What that means is that the closer this value is to zero, the more accurate your model. The next metric to talk about is the root mean squared error metric. This metric is the square root of the mean squared difference between the predicted and actuals. Now that's a mouthful, but what does that mean? Well, perhaps it's best to use an example. Imagine a model that predicts the price of a car again. Now let's say the actual price of a car is $1,000 and my model predicted $800. Well, the root mean squared metric would take the $1,000, subtract $800 for $200, and then it would square that value for $40,000, and then it would square root that value, bringing it back to $200. Now obviously that sounds useless, but that's because my example only uses one car. For this metric to make sense, you actually need to do an average of all the squares of all the differences between all the predictions and actuals. So if I had one car that was off by $200 and another that was off by $400, then I would square both, one for $40,000 and one for $160,000, average the two numbers for 100,000, and then do the square root of that, bringing us to about $316. Now, ultimately, we use this metric in comparison to the mean absolute error metric we talked about earlier. In fact, if your root mean squared error is larger than your mean absolute error, it can actually mean that there's a much greater variance in individual errors in your predictions. In other words, the bigger the number, the more sporadic and inaccurate your model is. Next, we have the relative squared error metric. This is an interesting metric for sure. First, it's a relative metric. It calculates a value between 0 and 1. You saw in the previous two metrics that the values were in the same units as what we're predicting. In this case, we're trying to calculate how close we are to the actuals without bringing units into the mix. Relative metrics are ideal because you can use them to compare different models that produce values in different units. So how does this metric work? Well, the relative squared error metric is determined using the square of the differences between actual values and predicted values. This metric looks to determine what the squared error is in a relative manner. The idea is to get the value between 0 and 1. Furthermore, the math tells us that the values that are closer to 0 are better. Basically, that means that there is very little error between the predicted and actual values, which is what we want. So if you think of the metric as a sort of percentage number, which it isn't, but it can help you wrap your head around it, then you can see that the larger the number, the worse your average prediction. Whereas the closer to 0, the much less error we have in the model, and thus the better the average prediction. And that brings us to the relative absolute error metric. This is very similar to the relative squared error metric, and just like RSE, it produces a relative number between 0 and 1. And that means that the metric that's produced is without units. So just like RSE, the relative absolute error metric can be compared with different models that produce different values in different units. The difference between relative absolute error and RSE is that the relative absolute error metric is based on absolute differences. For example, if my prediction was $800 and the actual was $1,000, then my difference is negative $200. Well, in absolute terms, I don't care if that's a positive or negative number. I'm still off by 200 if my prediction was 1,200. So once again, this metric looks at all the predictions compared to all of the actuals, calculates their absolute difference, and then puts it into a relative context between 0 and 1 across all the predictions. And just like the RSE metric, the closer the metric is to 0, the less error was encountered, and thus the better my model is at making predictions. Which brings us to the last metric. The coefficient of determination metric is probably the most common metric used. The metric is usually referred to as R squared. And just like the RSE and RAE metrics that we just talked about, the R squared metric also produces a relative metric between 0 and 1. And once again, that means that the value is unitless, and therefore can be compared against other models regardless of what units they use in their predictions. I've personally not had occasion to do this other than for bragging rights because I've not compared apples to dump trucks. But I'm sure there's plenty of examples out there where comparing models might be very useful. The purpose of the R-squared metric is to summarize the variances between actual values and predicted values. The R-squared value can be thought of as a percentage value. The point of this metric is to give you an idea of how many of the predictions fall within the expected results formed by a standard regression equation. The higher the number, the better. So in this case, unlike our previous relative metrics, better performing models return a value closer to 1, because that would mean that we're 100% within regression tolerance and with exact predictions. In very rare cases, the R-squared value can be negative, but that would mean that you have such an exceedingly bad model that maybe you're really comparing apples to dump trucks. So there you have it. When you're training a model, you can evaluate the results of all your predictions versus the real, true, and actual values to determine how good your model is. Obviously, you can eyeball the data to decide if your predictions are subjectively close, but by using these 5 metrics, you can apply mathematics to tell you just how close your model is at making accurate predictions. Then you can use these metrics to decide if you need to tweak your model or maybe even tweak your data. In this demo, we're going to add an evaluation module to a Microsoft Machine Learning Studio ML Designer pipeline. We'll see how the module attaches to a pipeline and why it attaches that way. We'll also talk about how an evaluation module is generally used and what it's for. Okay, so the first thing we need to do is navigate to our instance of the Azure Machine Learning Studio in our browser. So what we want to do in this demo is add a model evaluation module to an existing pipeline. To do that, we need to go to the ML Designer. So let's go ahead and click on the Designer option in the left-hand menu. Now, in the interest of time, I've created a few pipelines ahead of time. I've named them based on their purpose. I have a pipeline for training a regression model, a pipeline for training a classification model, and a pipeline for training a clustering model. For this demo, I'll choose to further augment the regression model pipeline as it'll be the easiest to walk through and explain. So let's go ahead and click on it. Good. Now we're presented with the ML Designer. On the canvas, I've already got a set of modules that do a bunch of things. Now, as I explained before, the purpose of this particular pipeline is to predict what the price of a car should be based on all sorts of other variables associated to cars. That includes mechanical specifications, horsepower, miles per gallon, and so on. The pipeline takes an original dataset, cleans it up, then feeds 70% of that data into a model trainer and uses a linear regression algorithm to come up with a price prediction algorithm. In our last demo, we attached the output of the model trainer, that being the trained model, to a model scoring module. Then we attached the remaining 30% of our original dataset to that same scoring module. The purpose of that module was to provide a mechanism to compare the actual data to predicted data. Then you can determine if your model is good enough. Now in this demo, we're going to further augment this pipeline by adding a model evaluation module to the pipeline. The problem with the scoring module is that it's somewhat subjective. You, as the consumer, can compare the predictions to the actuals and decide for yourself if the results are to your liking. The purpose of the model evaluation module is to help further analyze and interpret the results of the model scoring. To illustrate, let's go ahead and add the evaluation module. First, expand the model scoring and evaluation section of the asset library to the left of the canvas. Now find the evaluation model module and drag it onto the pipeline beneath the score model module. And now, as always, placement doesn't matter, but it really helps for readability if we place it at the bottom. Next, we connect the output of the score model module to the left input of the evaluate model module. The left input of the evaluate model module is labeled as the scored dataset. In fact, this is just like any other dataset except that there's a specific column of information that it's looked for. So while you could technically attach any dataset you like, it won't work properly unless you attach a scored dataset. And that's what the output of the scoring module is. Okay, so at this point the pipeline is configured to take a dataset about cars, augment that dataset so we're using valid and useful data, and then split that data such that 70% of the data goes towards training a prediction model for car pricing, and the remaining 30% of the data goes towards scoring the output of that model. We can then use the scoring module to manually compare predicted values versus actual values. However, we've added another module that will take the output of the scoring module and feed it to an evaluation module so that we can more definitively determine the effectiveness of the model training. And that's the main purpose of the evaluation module. What we want to do when we use the evaluation module is get some more definitive insights into the validity of our model. Once the pipeline runs, the output of our model training will be fed into our evaluator. Then we'll be able to explore the results of the evaluation based on a few different metrics. For example, the evaluation module gives us the mean absolute error value, which is the average difference between our predicted and actual values. The module also gives us the root mean squared error value, which is the square root of the mean squared difference between predicted and actual values. If this value is larger than the mean absolute error, it means that there's actually a greater variance in individual errors. Another value you get is the relative squared error. Now this is a value between 0 and 1, which is based on the square of the differences between predicted and actual values. Now this metric is good because the closer it is to 0, the better the model is doing. A similar value is relative absolute error. This is a value between 0 and 1 again, and it's based on the absolute difference between predicted and actual values. And once again, the closer the metric is to 0, the better the model is doing. And finally, one of the most common metrics is the R-squared metric. This metric summarizes how much of the variance between predicted and actual values is explained by the model. In this case, the closer the metric is to 1, the better the model is doing. In this demo, we're going to run a pipeline via Azure Machine Learning Studio. We're going to do that by opening up an existing pipeline and then submitting it to a new experiment. While the run is happening, I'll explain what each module is doing. We'll know we're completed the run when the final module has been executed and the pipeline run is shown as completed. Okay, so the first thing we need to do is navigate to our instance of the Azure Machine Learning Studio in our browser. So what we're going to do in this demo is execute a pipeline run into a new experiment. To do that, we need to go to the ML Designer. So let's go ahead and click on the Designer option in the left-hand menu. Now, in the interest of time, I've actually created a few pipelines already, and I've named them based on their purpose. I have a pipeline for training a regression model, a pipeline for training a classification model, and a pipeline for training a clustering model. For this demo, I'll choose the regression model pipeline that we've been using so far. It'll be the easiest to walk through and to explain. Good. Now we're presented with the ML Designer. On the canvas are all the modules that I set up previously, as well as the new modules that we added in the last couple of demos. Let's do a quick recap of what this pipeline is all about. First, the purpose of this pipeline is to create a model that accurately predicts the price of a car, based on a number of other variables. The future of this pipeline would ideally be to generate a model that can be used by external sources to accurately provide appropriate prices for cars. At the very top of the canvas, I have a dataset. This is a sample dataset for Microsoft that represents information about cars. There's all sorts of information about cars in that dataset. Things like horsepower, mechanical specifications, miles per gallon, so on. Importantly, it also includes information about what the price of each car actually is. Now, after the dataset, there's a few modules that transform the dataset, and we'll go into more detail about these as we perform the run. But at a high level, these transformers augment the dataset by removing undesired data and reducing bias on some of the remaining data values. Then, after the transformation of the dataset flows into a split data module. Now, this module takes 70% of the data from my dataset and sends it over to a train model module. And that's where the bulk of the magic in this pipeline happens. The train model module uses a linear regression algorithm to walk through 70% of the values from my dataset, which are chosen at random. And the purpose of the train model module is to evaluate the dataset that it's given to try to create an algorithm that can accurately predict what the price of a car should be. The results of the model training are then sent to a model scoring module, along with the remaining 30% of the data that we split. And finally, the results of the scoring are fed into a model evaluation module so that we can get some additional insights into how the model performed against the data that we fed it. Alright, so that's what our pipeline is supposed to do. So let's go ahead and actually do it. To execute a pipeline, we need to click on the Submit button in the top right of the designer. Now this pops up a dialog where we can choose to append the run results to an existing experiment, or we can create a new experiment altogether. In this case, since this is our first run, let's create a new experiment, and we can do that by clicking on the Create New Radio button at the top of the dialog. Of course, we need to give our experiment a name, and I'm going to name my experiment SB Test Pipeline Regression Experiment. Good. Now we can click Submit. Alright, now at the top of the screen, under where the Submit button was, you'll see an indicator that tells us that the pipeline is running, and that's a good sign. We also see right away that our first module is being queued. So it's going to start running right away too. Now this whole process will take many minutes, so I'll fast forward between each module. But let's talk about the modules as they run. Now the first module is the Select Columns in Dataset module. This module accepts the original dataset about cars as its input. The original dataset is a little flawed, so the data is not great for feeding into our model. So we want to cleanse it in a few ways. Well, one of the ways that we want to cleanse the dataset is to remove columns that we don't want. In fact, in the original dataset, there's a column that quite often has missing data in it. Missing data is useless to a model trainer. So the purpose of this module is to scrub that column from the dataset. Now we also get to see our linear regression module. This module prepares an algorithm to use in our model trainer. I left it as the default settings. In this case, the algorithm that's prepared is an ordinary least squares method with a very small L2 weight. We don't dwell on this module too much other than to say that there are lots of different algorithms that you can choose from, and each of them are tunable to your desires. The second transformation module is the Clean Missing Data module. This module accepts the dataset that has a bad column removed and now analyzes the data itself. In fact, when I configured this module, I asked it to look at a few columns that were prone to missing data. Then, if any rows of data in that dataset are found to be missing data in the columns that I selected, the entire row is removed. So the first module removed a column from the dataset, and this module removes rows from the dataset. The next module is the Normalized Data module. In the dataset, there are some columns with very large values and others with very small values. For example, RPMs is measured in the thousands, but miles per gallon is measured in the tens. These values are equally important, but the range in values might make the model trainer put more emphasis on the importance of the RPM column. So the purpose of the normalization module is to take certain columns that I select and make sure that they have all the same scale. And that eliminates any bias that the model might have towards certain values just because of their scale. Next, we get to our Split Data module. Now, as we've discussed, this module splits our freshly cleansed dataset into two subdatasets. The first subdataset is 70% of the dataset, and the second dataset is the remaining 30%. Now, it's worth noting that there are a few ways that you can configure this module. It doesn't just have to be a percentage split. You can split the dataset based on values or even expressions. In my case, I chose the percentage split. However, even with that, it's a random set of data that I'll get. And that means that every time I run this pipeline, I'll feed a different set of data into each subdataset. Finally, we've hit the model trainer. This module uses the prepared algorithm and ingests the 70% share of the cleansed dataset. The trainer will evaluate the data according to the algorithm and come up with a mechanism to predict the price value for each car in our dataset based on the data it sees in there. It'll search for the correlations. Maybe horsepower is the pivotal piece. Maybe horsepower combined with RPMs. Maybe miles per gallon is the surprise factor in predicting price. Regardless of what the various combinations are, the purpose of this module is to come up with a model that can predict price relatively accurately. With the model training complete, now we can execute the scoring module. This is taking the trained model and applying it to the remaining 30% of the dataset that we have. This module will then produce a new column of data in our dataset, and the new column is the predicted price. Later, when we inspect the data from this module, we'll be able to see the actual versus predicted values in a tabular format. And lastly, we have the Model Evaluation module. This is taking the scored dataset from the scoring module and running some additional metrics against that data. And this will give us a sense of the accuracy of our model. Alright, our run is finally completed. Now you can see all the modules are green and marked with a completed label. And at the top of the screen, the Submit button has returned. And beneath that, we have a label that says that the run is finished. That's it. That's all it takes to run a pipeline. Now you might remember that when we submitted our pipeline, we were asked to select or create an experiment. If you're ever curious as to where that is, you can actually click on the Experiments option in the left-hand menu. In fact, let's do it now. The Experiments screen has a list of all the experiments that we've ever run. In this list, we can see the experiment that I just run. So let's click on it. In the Experiment Details screen, we can see a few bits of information about our experiment. We can see all the runs that we've ever performed. We can look at some metrics about the run, and we can even view details about individual runs. Now this is getting a bit out of scope of this particular demo, but it's useful to see where all of your information is being kept so that you can refer to it later. Regardless, we've successfully performed a pipeline run. Great job! In this demo, we're going to go over what the results of a pipeline execution look like when they run through a model evaluation module. In this demo, I'll show you how to access the evaluator output data and logs. We won't go into too much detail about the results themselves. Instead, we'll focus on where you can find that information. Okay, so the first thing we need to do is navigate to our instance of the Azure Machine Learning Studio in our browser. So this demo assumes that you've executed a pipeline and that your pipeline had an evaluate model module in it. In my case, I'll use the same regression pipeline that I ran in the previous demos. Remember that the purpose of that pipeline was to take a dataset of information about cars and train a model to predict prices for cars. The model evaluation module is used to determine just how effective our model ended up being. So we need to look at the insights calculated by the evaluation module to see that. There are two ways that we can access evaluation datasets. Let's start with the easiest one. The easiest way to access evaluation data is to use the ML Designer. So let's go ahead and click on the Designer option in the left-hand menu. Now I'll go ahead and open my regression pipeline since that's where I ran my experiment last. Good. So now we see the pipeline canvas. Now notice how all the module boxes are green with a completed label. At the top of the page, beneath the Submit button, there's a label that says that the run finished. That's actually a key term here, run. The fact is that every time we execute the pipeline, we're asked to add it to an existing experiment or to create a new experiment. And when we execute the pipeline, we're adding what's called a run to that experiment. The ML Designer will always show information about the most recent run. Well, actually it'll show information about all the most recent runs as long as nothing in the pipeline has actually changed, but that's a detail. So as we can see from the canvas, we had an original dataset about cars, then we ran that dataset through a transformer and removed unwanted columns, then the dataset had some rows with missing data removed. After that, certain bits of information were normalized to a common scale to reduce bias, and once the dataset was prepared, it was split into two sub-datasets. 70% of the data went towards training a linear regression model, and the remaining 30% went towards scoring the trained model. Finally, at the bottom of the canvas, we see a module that's used to take the scored model output and evaluate it. And that's the module we're interested in. So let's click on it to select it. Now you'll see the configuration panel appear on the right-hand side of the canvas. In the panel, we see a few tabs, and we can use each tab to configure the module or view some detailed information. In our case, what we're most interested in is the results of the evaluation. To see that, we need to first go to the Outputs and Logs tab, so let's click on that. Now the Outputs and Logs tab shows us the results of the model evaluation. Now remember, this is for the most recent run. If you ran this pipeline a bunch of times, you wouldn't necessarily be able to see all of the past runs. Well, actually more accurately, you wouldn't be able to see the past runs where something about the pipeline changed. Now that being said, What you are seeing in this panel is a dataset at the top called Evaluation Results. Then there's also a bunch of other log files at the bottom. If you click on the logs and scroll to the right, you can actually view the logs, but this is a really small panel and not very useful even if you resize it. But that's okay though, because what we're most interested in here is the Evaluation Results dataset. Now the dataset has 3 buttons on it. You can register the dataset, and what that means is that you can actually save the dataset as a usable dataset in ML Studio. And that would of course mean that you could use the dataset in other pipelines. You can also view the raw dataset, and this will actually open up a blob storage account for you to view. And this can be handy, but it's worth noting that this is also really deep into the weeds and probably not worth it for an evaluation dataset. Now the last button is for visualizing the dataset. Now this is what we want, so let's go ahead and click on it. In the visualization pop-up, we're shown the actual evaluation results. This might actually look really anticlimactic, but this is actually really useful information. We'll get into more detail about what each of these numbers mean in a later demo, but let me go over it really quickly. Each of the 5 columns of information evaluate the results of our scored model to determine the effectiveness of that model. The mean absolute error tells us the average difference between our predicted and actual values. The root mean squared error tells us the square root of the mean squared difference between the predicted and actual values. The relative squared error is a value between 0 and 1, which is based on the square of the differences between predicted and actual values. The relative absolute error is a value between 0 and 1 again, and is based on the absolute difference between predicted and actual values. And finally, the coefficient of determination, or R squared, is the variance between predicted and actual values. Again, we'll get into the actual numbers in another demo. In the meantime, this is how you access that information from the latest run. But what if you ran your pipeline a bunch of times with slight variations in the pipeline? What if you wanted to see the results of other runs, not just the latest? Well, remember that each pipeline execution is attached to an experiment. So the way to see other runs is to go look at the experiments themselves. So let's click on the Experiments item in the left-hand menu. Now the experiment screen shows us all of our experiments, and in my case I only have the one experiment. You may have many experiments, so find the experiment you ran and let's go ahead and click on it. Now the experiment details screen shows us a few metrics about our experiment and all the runs that have been executed. In fact, the bottom of the page is a list of all the runs that have been performed against this experiment. Now in my case, I've only run this pipeline once against this experiment, so I only have one run listed here. Regardless, let's go ahead and click on the run. Now the first thing we see when we open up the run is a Graph tab. The Graph tab happens to show us our pipeline canvas again. More importantly, this is what the pipeline canvas looked like when this run was executed. If the pipeline looks different now, that's not what we'd see here. So this gives us a good indication of context when we look at our run. Now that's not what we're interested in here though. What we're interested in is the evaluation results, right? Well, just like the ML Designer, you need to click on the Evaluate Model module in the canvas. Now notice that once again a panel appears on the right-hand side, and that includes information about the module. And just like before, there's an Outputs and Logs tab. So let's make sure that that's selected. Now once again we see the evaluation results and the logs. And the panel is a bit bigger than the one in the ML Designer, so you can see the logs a bit better here. But regardless, our real intent was always to look at the dataset, and there it is once again at the top of the panel. So there you have it, the evaluation results. You can access the most recent results from the most recent run via the ML Designer, but you can also access the results from all the runs via the Experiments view. In this demo, we'll dive into the evaluation results of a regression pipeline run using Azure Machine Learning Studio. We'll compare the results of 2 different runs and determine what each metric is telling us about our trained model. At the end of the demo, we'll decide which run will give us the better model. First, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do here is take a look at our model run results and determine how effective our model training was. But before we begin, I've added a bit of a twist. Remember that the pipeline we've been dealing with is all about predicting the price of a car based on a bunch of other metrics. At one point in our pipeline, I randomly split the input data so that some of it is used to train a model and the rest of it is used to score the model. What that means is that every single time I run my pipeline, I could get a different model that is better or worse at predicting prices. So what I've done here is I've run my pipeline again so that we have two runs. In this demo, I want to evaluate the results of my first run and then compare the results to my new run. Then I want to decide which of the two models I prefer. Okay, so you'll recall from our previous demo, if you want to access the results of multiple past runs, you need to use the Experiments section. So let's go ahead and click on the Experiments option in the left-hand menu. Now here we see a list of all of our experiments. For me, I care about the regression experiment I ran, so I'm going to go ahead and click on that. Now once again, we're presented with a screen that gives me all of the metrics about my experiment and all the runs included therein. What we're going to do in this demo is we're going to actually look at each of the runs and explore the evaluation results to determine how effective the model in each run was. Then we'll decide which of the two models is our preferred one. So let's go ahead and click on the first run. Good. Now here's our canvas that shows us how our pipeline was configured. Now let's go ahead and click on the Evaluation Model module so that we can see the details about it. Now let's make sure that we've selected the Outputs and Logs tab. And now let's visualize our evaluation results by clicking on the Visualize link in the Evaluation Results dataset at the top of the tab. Okay, so here we have 5 metrics that have been calculated based on our model training and the subsequent scoring that happened. Now each of these 5 metrics means something, so let's go over each number and what they mean for how effective our model training was. First, we have the mean absolute error metric, and this metric represents the average difference between predicted values and actual values. So in this case, we're seeing the average difference between the actual price of a car and the predicted price of the car. For this particular model, our prediction is off from the actual by about $1,955. Obviously, we want the number to be as close to zero as possible. Now, as a quick aside here, remember that sometimes information is subjective. Often we pay more money for brand name than we do for actual mechanical specifications. So while this number says our predictions are off, it could also just as easily mean that the prices of these cars are as arbitrary and really not based on anything at all. Anyway, next we have the root mean squared error metric, and this metric represents the square root of the mean squared difference between the predicted and actual values. Now this value is in the same units as the value we're predicting, so in this case dollars. This metric is best compared with the mean absolute error metric that we just went over. If the value is larger than the absolute error metric, then it indicates that there was a greater variance in individual errors, which there was in this case. Next, we have the relative squared error metric. Now this metric is a relative value between 0 and 1 and is based on the square of the difference between predicted and actual values. So in this case, the closer the value is to 0, the better our model is doing. Now this metric has no units either, so this means that you can compare the model to other models regardless of units. In our case, our value is 0.08, so that's not too bad. Then we have the relative absolute error metric. This metric is also a relative value between 0 and 1, and is based on the absolute difference between predicted and actual values. So once again, the closer the value is to 0, the better the model is doing. In this case, our value is 0.24, which isn't great. And finally, we have the coefficient of determination metric, and this is usually called the R-squared metric. Now this metric summarizes how much of the variance between predicted and actual values is explained by the model. Unlike the previous metrics, in this case, the closer the value is to 1, the better the model is doing. So looking at these metrics, it doesn't look like our model is doing too badly. It seems reasonably good at predicting prices, and there are definitely outliers. That can mean there's a problem with the data, or it can mean there's problems with the model. Either way, we're reasonably satisfied. But now we want to compare that to another model run. So let's do that. Now let's make our lives a little easier and leave this window open. Then let's duplicate our browser tab by right-clicking on the tab and selecting Duplicate. Good, now that's brought us back to our run window with the same experiment. But we want to look at a different run, right? So at the top of the screen there's a breadcrumb, so let's go ahead and click on our experiment name. And here we are back at the experiment details page. Now let's go ahead and choose our most recent run. And once again, let's click on the Evaluate Model module. And let's make sure to open the Outputs and Logs tab. And now let's visualize the evaluation results of this model run. Good, now once again we see the evaluation results window with those 5 metrics. In this case, the MAE is 1,857, the RMSE is 2,660, the RSE is 0.11, the RAE is 0.33, and the R-squared value is 0.88. But how does that stack up to our other run? Well, let's toggle between these two browser tabs and find out. In our first run, the MAE was 1,955, and in our latest run, the MAE was 2,660. Since we want this value to be as close to 0 as possible, that would mean that by this metric, our first run produced a better model. In our first run, the RMSE was 2,892, and in our latest run, it was 2,660. And again, we want this value to be as close to 0 as possible, so that suggests that our last run produced a better model, or at least less sporadic. In our first run, the RSE was 0.08, and in our latest run, it was 0.11. Now this is a relative metric between 0 and 1, and those that are closer to 0 are better, so that would suggest that our first run produced a better model. And in our first run, the RAE was 0.24, and in our latest run, it was 0.33. And just like RSE, this is a relative metric between 0 and 1, where a value closer to 0 is better. So that suggests that our first run once again produced a better model. And finally, in our first run, the R-squared value was 0.91, and in our latest run, it was 0.88. Now once again, this is a relative metric between 0 and 1, but this time a value closer to 1 is better. So once again, that suggests that our first run produced a better model. So what are these metrics telling us overall? Well, they're telling us that our first run appears to have produced a better and more accurate prediction. What it also tells us is that different runs can produce different results. So it's a good idea to send in multiple datasets and to train and score your models. Then you can evaluate each model result just like this to determine which one produced the most accurate results. And then that's the model that you can deploy down the road. In this demo, we're going to go back and take a look at our scoring results from our model runs in Azure Machine Learning Studio. We'll explore where to find the results and what the information can tell us. Then we'll explore the different pipeline runs to see if we can tell which model produced better results. First, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do here is take a look at our model run results and determine how effective our model training was from a scoring perspective. First, remember that the pipeline that we've been dealing with is all about predicting the price of a car based on a bunch of other metrics. At one point in our pipeline, I randomly split the input data so that some of it is used to train a model and the rest of it is used to score the model. And what that means is that every single time I run my pipeline, I could get a different model that is better or worse at predicting price. So what I've done is I've run my pipeline again so that we have 2 runs. Now in this demo, I want to take a look at the model scoring for my first run versus the latest run, and then compare the scores. Then I want to decide which of the 2 models I prefer. Of course, we already did this by looking at evaluation results, so what we're going to do here is look at the raw scores and see how it's actually tougher, or at least more subjective, to make a determination based just on the scoring. Alright, so as you'll recall from our previous demos, if you want to access the results of multiple past runs, you need to use the Experiments section. So let's go ahead and click on the Experiments option in the left-hand menu. Now here we see a list of all of our experiments, and for me I care about the regression experiment I ran, so I'm going to go ahead and click on that. And once again, we're presented with a screen that gives us some metrics about my experiment and all the runs that were included therein. What we're going to do in this demo is we're actually going to look at each of the runs and explore the scoring results and see if we can determine how effective the model in each run was. Then we'll try to decide which of the 2 models is our preferred one. So let's go ahead and click on the first run. Good. Now here's our canvas that shows how our pipeline was configured. Now let's go ahead and click on the Score Model module so that we can see the details about it. Good. Now let's make sure that we've selected the Outputs and Logs tab, which I have. And now let's visualize our scoring results by clicking on the Visualize link in the Scored Dataset at the top of the tab. Okay, so here we have every column from the dataset that was passed into the scoring module. Now remember that we have a split data module in our pipeline that feeds 30% of the cleansed data into the scoring module. So right at the top of the pop-up, we can see that the dataset has 60 rows in it. And that means that 60 rows were used to score the trained model. Then what we see in the bulk of the pop-up is all of the columns from the scored dataset. So let's scroll the list all the way to the right. Now you'll notice in the dataset that there's a column called Scored Labels, and that's the key column in all of this. In reality, what the Scored Model module does is take the input dataset and run it against the trained model. The trained model then takes the input data and tries to predict a price for each row of data that it's given based on the algorithm it came up with using the other 70% of the data. The Score Model module then takes the predicted values for each row and adds them to the Scored Labels column. So what we're seeing in that column is the actual predicted results from the trained model based on the data presented in each row. Meanwhile, to the left of the Scored Labels column happens to be our price column. This is the actual price of the car defined by each row. And that means that what we have here is the predicted values in the Scored Labels column and the actual values right beside them in the price column. And that means that we can actually look at the values and decide for ourselves if we feel that the data looks okay. And if we scroll down the list, we can see that some predictions are pretty close, and some appear to be way off. Now that could mean that our model is bad, but it could also mean that our input data is bad. For example, if we find that one of our predictions is really off, we might find that that ends up being typical of a certain brand of car. Maybe we determine that there's a bit of a price hike there because of a recent fad. Based on our visualization of the data, we might choose to augment our dataset versus suggest that our model is terrible. Now we can also click on the columns for more insight. So for example, let's click on the price column. When we look at that column, we can see the mean, the min, the max, and standard deviation. And down at the bottom, we can see a distribution chart. You can also see a small version of that chart in the column header. Now let's click on the Scored Label column. Now here we see the same bits of information with the mean, the min, the max, and so on. Now again at the bottom we see a distribution chart. It's worth noting that the distribution chart looks different between the predicted and actual values, and that's an immediate indicator that the values are different, if only slightly. Regardless, in looking at this model, the numbers don't seem too bad. So let's go compare that to another model. To do that, we need to look at our other pipeline run. So let's do that. And again, let's make our lives a bit easier and leave this window open, and let's duplicate our browser tab by right-clicking and selecting Duplicate. Good. Now this is bringing us back to our run window for the same experiment. But we want to look at a different run. So at the top of the screen is a breadcrumb, and let's go ahead and click on our experiment name. And here we are back at the experiment details page. So let's go ahead and choose our most recent run. And once again, let's click on the Score Model module. Make sure that the Outputs and Logs tab is selected. And now let's visualize the scored dataset for this model run. And once again, let's scroll all the way to the right so that we can see our predicted versus actual columns. Now once again, we see a column of information called price, which is our actual values, and another column called scored labels, which is our predicted values. And once again, we can scroll through all those values and see some pretty close and some that are pretty way off. In fact, we can see once again that our distribution charts at the top of each column shows a slight discrepancy between the predicted values and the actual values. But how do we compare that to our other run? Well, we can toggle between our tabs. But that doesn't really show us which one is better, does it? In fact, we can look at the raw data and we can look at some of the metrics like standard deviation, and we can decide which model is better. But as you can tell, that would probably be based in large part on your own gut feelings. And that's why the model evaluation module is so much better for this. Of course, you can export the dataset and apply other algorithms to it. You can even use this dataset as the input to another pipeline. But one thing's for sure, looking at this raw data is tedious and prone to issues, and we're only talking about 60 rows of data. Imagine if it was thousands or millions. From our last demo, we were able to relatively easily tell that the model from our first run was better at making predictions. When we look at the results of our scored model, we have a much harder time coming to that conclusion. Regardless, this is how you access the information for a scored model. In this demo, we're going to go over regression model training in Azure Machine Learning Studio. We'll talk about what a regression model is, when to use it, and then I'll explore the output data and what it's really telling us. Now first, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do is take a look at a pipeline that trains a regression model. Now I've prepared a few pipelines ahead of time so that we can walk through it. To look at a pipeline, we need to head over to the Designer area of the ML Studio. So let's click on the Designer option in the menu. Now this screen shows us all of the pipelines that we've created in ML Studio. In my case, I've pre-created 3 pipelines so that we can talk about some of the different kinds of model training that you can do. In this case, we want to talk about training a regression model. So I'm going to go ahead and click on my SB Test Pipeline Regression pipeline, since that's the one that has my regression model training. Perfect. Now what we see here is the ML Designer page for my regression model training pipeline. Right in the middle of the screen, we can see a canvas that has a bunch of modules on it. I'm going to go over those in a second, but first I want to talk about what a regression model is. Primarily, a regression model is a type of machine learning that's used to predict some values of an item based on various features of that item. Importantly, the value you're training to predict is always a number. In this particular pipeline, the item we're talking about is a car, and the value we're trying to predict is its price. We can use the various features of each car to determine an algorithm for predicting the price. For example, you could apply features like horsepower, number of seats, engine size, miles per gallon, and a whole host of other features to decide what a likely price is for that car. When we're implementing regression model training, we're actually implementing a supervised machine learning technique. And what that means is that we're training the model by giving it the actual answer. So the model learns to create an algorithm that tends to fit the pricing data. So imagine I give a model things like horsepower, number of seats, and engine size, and then tell it to come up with a price. It would have no baseline to determine what a valid number would be. Does $45 billion sound good? Well, no, that sounds kind of dumb. So we give the model some prices along with the features about the item, and then it's able to create an algorithm that comes up with a relatively accurate prediction that tends to fit the data. So with that known, let's take a look at our pipeline and see how that fits with the regression model training description I just gave. Now at the very top of the canvas, I have a dataset. This is a sample dataset from Microsoft that represents information about cars. And just like I said, there's all sorts of information about cars in that dataset. Things like horsepower, number of seats, various mechanical specifications, miles per gallon, and so on. And importantly, that dataset includes information about what the price of each car is. After the dataset, there's a few modules that transform that dataset. In order for regression model training to produce a good prediction, it's important that it's fed good data. The better the data, the better the results. So use transformers to weed out bad data. The first transformation module removes a particular column of information from the dataset. Microsoft's dataset includes a column that has a lot of missing data in it, and that would complicate and confuse the model training, so it's best to just remove the column. If the first transformation module removed a bad column, the second transformation module removes bad rows. Once we remove the bad column, there are a few rows that have some missing data, so this module is configured to remove those rows. Next, we get a normalization module. Some of the data in the dataset is large, and some of it is small. For example, RPMs is measured in the thousands, while miles per gallon is measured in the tens. To avoid the model trainer giving some bias to large numbers versus small, the normalizer brings selected columns to the same scale so that they can be assessed with the same weighting. Then, after the transformation of the dataset flows into a split data module. This module takes 70% of the data from the freshly cleansed dataset and sends it over to the train model module. And that brings us to the model training. Now you'll see that the model trainer has a linear regression algorithm attached to it. You see, the model trainer trains a model based on an input dataset, but it needs to be told how to train that model. And that's where the input algorithm comes in. In fact, there's lots of different kinds of algorithms depending on the type of data you're dealing with. For regression models, there are 6 built-in algorithms that you can use. The first is our linear regression algorithm, which uses a simple linear regression method for calculating weight of various dataset features to predict an output. There's also the decision forest regression, and that creates a bunch of decision trees to make binary decisions to arrive at the correct answer. And next there's a boosted decision tree regression algorithm. And this is similar to the decision forest regression, but it uses boosting. The algorithm is considered boosted because each regression tree is dependent on previous trees, and the algorithm learns by fitting the residual of the trees that preceded it. Then we have the fast forest quantile regression. This helps with understanding more about the distribution of the predicted value, rather than just getting a single mean prediction value. Next is the neural network regression, and you can use this module to create a customized algorithm. And finally, there's a Poisson regression. Poisson regression is typically used for predicting numeric values, like counts. Now finally, once our model is trained, the output is fed to a model scoring module along with the remaining 30% of the cleansed dataset. The scoring module then executes the trained model against the dataset and adds a new column of information that is the predicted price, and this allows us to look at the actual price compared to the predicted price. And finally, the results of the scoring are sent to a model evaluation module where we can actually compare the predicted versus actual price and determine just how good the model we trained is at predicting the price for vehicles. Okay, so to recap, we're trying to predict what the price of a car should be based on some features of a car. Well, the output value is numeric, so a regression model sounds like the right thing to use. And also we're using the features of the car to make that prediction. So once again, regression sounds like the right thing to do. So what we've done here is implemented a supervised pipeline that feeds known data into a model trainer so that it can create an algorithm based on that regression approach to predict a price based on known prices. The algorithm should create an algorithm that best fits the given data. Then, because we're keeners, we're testing the output of that model against another known data set so that we can see how good our model is. Well, that sure sounds right. So the next thing that we can do is run the pipeline and check out the results. Well, as you can see, we've already run the pipeline. We can see that because each box is green and has a completed label. So what we can do is we can click on the Evaluate Model module and check out the results of our run. So let's do that. On the right-hand side of the display is the configuration panel for the evaluation module. And this gives us all sorts of detail, but what we're mostly interested in is the results of our run. So let's make sure we've got the Outputs and Logs tab selected. And now let's open the evaluation results at the top of the tab by clicking on the Visualize button. Now this pop-up gives us some metrics about our model training. What this tells us is how accurate our model is. Put another way, this is how close the prediction was to the actuals. And we can look at these numbers and decide if our model is good enough to put out into the wild as a mechanism for predicting what the price of a car should be. For me, here's how I interpret these numbers. The mean absolute error value is the average difference between predicted and actual values. It's measured in dollars just like our price, but in this case, we're not off by a whole heck of a lot. So this model seems okay at first blush. The relative squared error value is a relative value between 0 and 1. The closer to 0, the better. In this case, we're pretty close to 0, but I feel like we could be better. And the relative absolute error value is similar in that it's a relative value between 0 and 1, where 0 is best. In this case, we're even further from 0, so I'm not really feeling very confident in this one. And finally, the R-squared value, the last column, is another relative value between 0 and 1, where 1 is best. In this case, we're pretty high up, but it's still not great. At the end of the day, we can look at these values and we can say that our model is not bad at predicting prices, but it could certainly be better. If your doctor came up to you and said that he was 90% sure that you were healthy, that's an area where you might be okay with the assessment, but you'd definitely be happier if it was a bit more certain. So we'd look at these model numbers and see if we could improve our accuracy. Now we could do that with better data, or we could do that by tweaking the algorithm. There's lots of different things you can do, but with the evaluation in place, you now have all the tools that you need to handle a regression pipeline. In this demo, we're going to go over classification model training in Azure Machine Learning Studio. We'll talk about what a classification model is and when to use it, and then we'll explore the output data and what it's really telling us. First, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do is take a look at a pipeline that trains a classification model. Now I've prepared a few pipelines ahead of time so that we can walk through it. To look at a pipeline, we need to head over to the Designer area of the ML Studio. So let's click on the Designer option in the menu. Now this screen shows us all of the pipelines that we've created in ML Studio. In my case, I've pre-created 3 pipelines so that we can talk about some of the different kinds of model training that you can do. In this case, we want to talk about training a classification model. So I'm going to go ahead and click on my SB Test Pipeline Classification pipeline, since that's the one that has my classification model training. Perfect. Now what we see here is the ML Designer page for my classification model training pipeline. Right in the middle of the screen, we can see a canvas that has a bunch of modules on it. I'm going to go over those in a second, but first I want to talk about what a classification model is. Primarily, a classification model is a type of machine learning that's used to predict some category or class to which an item belongs. In this particular pipeline, the classification we're talking about is diabetes, and whether or not a person is diabetic. For example, you could apply the features of a patient like age, weight, blood pressure, and a whole host of other features to decide the likelihood that a patient is diabetic. In this case, the classification is diabetic or not diabetic. When we're implementing classification model training, we're actually implementing a supervised machine learning technique. What that means is that we're training the model by giving it the actual answer. So the model learns to create an algorithm that tends to fit the diabetic data. So imagine I give a model things like age, weight, and blood pressure, and then tell it to tell me if the patient is diabetic. It would have no baseline to determine what a valid classification would be. So we give the model the answer along with the features about the patient, and then it's able to create an algorithm that comes up with a relatively accurate prediction that tends to fit the data. So with that known, let's take a look at our pipeline and see how this fits with the classification model training description that I just gave. Now at the very top of the canvas, I have a dataset. And this is a sample dataset from Microsoft that represents information about patients that may or may not have diabetes. And just like I said, there's all sorts of information about patients in that dataset. Things like age, weight, blood pressure, and so on. And importantly, that dataset also includes information about whether the patient is diabetic. After the dataset, there's a single module that transforms the dataset. In order for classification model training to produce a good prediction, it's important that it's fed good data. The better the data, the better the results. So we use transformers to weed out bad data. The transformation module we use is a normalization module. Some of the data in the dataset is large and some of it is small. For example, the number of pregnancies is usually under 10, while plasma glucose edges at around 100. To avoid the model trainer from giving more bias to the larger numbers versus the small, the normalizer brings selected columns to the same scale so that they can be assessed with the same weighting. Then, after the transformation of the dataset flows into a split data module. Now this module takes 70% of the data from the fractionally cleansed dataset and sends it over to the train model module. And that brings us to the model training. Now you'll see that the model trainer has a two-class logistic regression algorithm attached to it. You see, the model trainer trains a model based on an input dataset, but it needs to be told how to train that model. And that's where the input algorithm comes in. In fact, there's lots of different kinds of algorithms depending on the type of data you're dealing with. For classification models, there are 12 built-in algorithms that you can use. One of them is our two-class logistic regression algorithm, which is used to predict 2 and only 2 possible outcomes. We're using this module because 2 classes is exactly what we want. The patient is either diabetic or not. In fact, there are multiple 2-class algorithms. This includes average perceptron, boosted decision tree, decision forest, neural network, and support vector machines. What you might notice about that is that these algorithms are very similar to regression algorithms, which is exactly right. These algorithms are using features of items to calculate a numeric classification system. While the output for us is diabetic or not diabetic, the actual output is 1 or 0. Of course, if there are 2-class algorithms, then clearly there are also algorithms that can predict more than 2 classes. In this case, we have similar regression algorithms again, but in this case, you need to provide additional details and the math is much more complicated beneath the hood. Finally, once our model is trained, the output is fed to a model scoring module along with the remaining 30% of our original dataset. The scoring module then executes the trained model against that dataset and adds 2 new columns of information. One column is whether the patient is or isn't diabetic, and the other column is the probability of that being true. That allows us to look at the actual diabetic state compared to the predicted diabetic state. And finally, the results of the scoring are sent to a model evaluation module which can actually compare the predicted versus actual diabetic state and determine just how good the model we trained is at predicting whether a patient is diabetic. Okay, so to recap, we're trying to predict whether a patient is diabetic based on some features of a patient. Well, the output is effectively yes or no. So a 2-class classification model training algorithm sounds like the right thing to use. Also, we're using the features of a patient to make that prediction. So once again, a type of regression algorithm sounds like the right thing to do. So what we've done here is we've implemented a supervised pipeline that feeds known data into a model so that it can create an algorithm based on that classification approach to predict whether a patient is diabetic based on known diabetic information. The algorithm should create an algorithm that best fits the given data. Then, because we're keeners, we're testing the output of that model against another known data set so that we can see how good our model is. And that sure sounds right. So the next thing that we would do is run the pipeline and check out the results. Well, as you can see, I've already run the pipeline. And we can see that because each box is green and has a completed label. So what we want to do is click on the Evaluate Model module and check out the results of our run. So let's do that. On the right-hand side of the display is the configuration panel for the evaluation module. This gives us all sorts of detail, but what we're most interested in is the results of our run. So let's make sure we've got the Outputs and Logs tab selected. And now let's open the evaluation results dataset at the top of the tab by clicking on the Visualize button. Now this pop-up gives us some metrics about our model training. What this is telling us is how accurate our model is. Put another way, this is how close the prediction was to the actuals. And we can look at these numbers and charts and decide if this model is good enough to put into the wild as a mechanism for predicting whether patients are or are not diabetic. But for the sake of this demo, let's take a look at one chart in particular. This chart is the confusion chart. It's the one that looks like a checkerboard. The chart has two axes and two values each. Along the top is the actual classifications, 0 or 1, and along the side is the predicted classifications, again, 0 or 1. All the data from the scored dataset is represented in this little chart as counts. For example, all the patients that were predicted to be diabetic and were actually diabetic are counted in the top left corner. Meanwhile, all the patients that were predicted to not be diabetic and actually were not diabetic are in the bottom right corner. And these corners represent accurate predictions from our model. Meanwhile, the top right and the bottom left corners represent the count of patients where predictions did not match the actuals. So what we can see here is actually a pretty good guess from our model. At the end of the day, we can look at these values and we can say that our model is pretty good at predicting whether a patient is diabetic, but maybe it could be better. But there's another way you can choose to look at this result. Sure, our model could be better. We could do that by tweaking the algorithms or putting in some better data. But what this might be saying is that some of our patients that we thought were or weren't diabetic actually were misdiagnosed. In fact, with AI, that's been known to happen from time to time. Given sufficient training, AI has been known to find issues, particularly in the medical field, that humans missed. So just because the model isn't necessarily nailing the actuals, doesn't mean that the model is actually wrong. Regardless, this is the way that you can put together a classification model. In this demo, we're going to go over clustered model training in Azure Machine Learning Studio. We'll talk about what a clustered model is and when to use it, and then we'll explore the output data and what it's really telling us. First, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do is take a look at a pipeline that trains a clustering model. Now I've prepared a few pipelines ahead of time so that we can walk through them. To look at a pipeline, we need to head over to the Designer area of the ML Studio, so let's click on the Designer option in the menu. Now this screen shows us all the pipelines that have been created in ML Studio. In my case, I've created 3 pipelines so that we can talk about some of the different kinds of model training that you can do. In this case, we want to talk about a clustering model. So I'm going to go ahead and click on my SB Test Pipeline Clustering Pipeline, since that's the one with my clustered model training. Perfect. Now what we see here is the ML Designer page for my clustering model training pipeline. Right in the middle of the screen, we can see a canvas that has a bunch of modules on it. And I'm going to go over those in a second, but first I want to talk about what a clustering model is. Primarily, clustering is a type of machine learning that's used to group similar items from a dataset based on various features of those items. Importantly, what you're trying to do is find a logical grouping for the items in the dataset. In this particular pipeline, the item we're talking about is a penguin. What we're trying to do is group all the penguins in the input dataset into 3 logical groups. We can see the various features of each penguin to determine an algorithm that can group penguins into appropriate clusters. For example, you could apply features like flipper length, body mass, and a whole host of other features to decide what a likely grouping is for the penguins in the dataset. When we're implementing a clustered model training, we're actually implementing an unsupervised machine learning technique. What that means is that we're training the model to group our data based on its features without knowing what the actual answer is. So the model learns to create an algorithm that groups items together into what it considers to be logical groups. We can assess that, but we really have no idea what those groups are going to be. So in this case, that means that we want to avoid giving the model obvious groupings like species or color, but really you can leave anything you want. The goal of this model is to say, hey, given a set of data, I want you to always group that data into 3 apparent logical groups. So with that known, let's take a look at our pipeline and see how that fits with the clustered model training description I just gave. Now at the very top of the canvas, I have a dataset. Now this is a sample dataset from Microsoft that represents information about penguins. And just like I said, there's all sorts of information about penguins in that dataset. Things like flipper size, body mass, and so on. Now after the dataset, there's a few modules that transform the dataset. In order for our clustering model training to produce an interesting logical grouping, it's important that it's fed good data, and that data doesn't have anything obvious in it. The better the data, the better and more interesting the results. So we use transformers to cleanse the data. The first transformation module removes the species column of information from the dataset. That's obviously useful information, but it would be a totally unfair bias to give to the model. We want 3 logical groups. Well, with species in the mix, that's probably pretty easy, so it's best to just remove that column. The second transformation module removes bad rows. Some of the data in the dataset is missing. So we've added this module to look through the data, and anywhere where there's missing data, that row is removed. Having missing data can make the model give bad answers. Remember, the better the data, the better the result, and that means having as much verbose data as you can get your hands on. And finally, we get to a normalization module. Some of the data in this dataset is large and some of it is small. For example, flipper length is measured in the hundreds, while body mass is measured in the thousands. To avoid the model trainer from giving more bias to larger numbers versus small, the normalizer brings selected columns to the same scale so that they can be assessed with the same weighting. Then, after the transformation of the dataset flows into a split data module. This module takes 70% of the data from the freshly cleansed dataset and sends it over to the train clustering model. This module takes 70% of the data from the freshly cleansed dataset and sends it over to the train clustering model module. And that brings us to the model training. Now you'll see we're using a different type of model trainer than we did before. The reason for that is because this trainer knows that its job is to create clustered data, so it can format the results accordingly. You'll also notice that the model trainer has a k-means clustering algorithm attached to it. Now obviously the model trainer trains a model based on the input data, but it does need to be told how to train that model. And that's where the input algorithm comes in. Now that being said, Microsoft has only one built-in algorithm that you can use for clustering. But that's okay, because the k-means algorithm is the simplest and best known algorithm for unsupervised clustering. Now there's a lot of different ways you can configure it, and I left everything as defaults and just asked for 3 clusters. But you can choose different versions of the algorithm as well as how many iterations over the data to perform before coming to a conclusion. In my case, I'm doing 100 iterations. Finally, once our model is trained, the output is fed into a module that will execute the algorithm against the remaining 30% of the cleansed dataset to logically group whatever's in that dataset based on what it learned from the first 70%. And finally, the clustered data is sent to a model evaluation module where we can actually start to take a look at what our outputs are. Okay, so to recap, we're trying to find 3 logical groupings for penguins based on some features of a penguin. Well, the output is 3 clusters of data, so a clustered model sounds like the right thing to use. Also, we really have no idea what the grouping should be, so the unsupervised nature of the run really does sound like a clustering model. So what we've done here is in fact implemented an unsupervised pipeline that feeds the data into a model so that it can train an algorithm based on various features of penguins to create 3 logical groups of penguins. The algorithm should create an algorithm that best groups the given data. Then, because we're keeners, we're testing the output of that model against another dataset so that we can see what it produces. And that sure sounds right. So the next thing that we would do is run the pipeline to check out the results. Well, as you can see, I've already run the pipeline. And we can see that because each box is green and has a completed label. So what we can do is click on the Evaluate Model module and check out the results of our run. So let's do that. Now on the right-hand side of the display is the configuration panel for the evaluation module, and this gives us all sorts of detail, but what we're most interested in is the results of our run. So let's make sure we've got the Outputs and Logs tab selected. And now let's open the evaluation results dataset at the top of the tab by clicking on the Visualize button. Now this pop-up gives us all sorts of metrics about our model. Now this can tell us if our model is any good. We actually had no expectations for what sort of grouping our model would even find, so we can't immediately say whether what we're seeing is right or wrong. So what we have to do is evaluate everything we see in this pop-up and decide what's up. First, we can see from the result description column that there are 3 clusters. They aren't named, obviously, but at least we know we have 3 groups. The average distance to other center, average distance to cluster center, and maximal distance to cluster center metrics tell us how penguins in the cluster fit in that cluster compared to other clusters or even within their own cluster. Now this can get pretty complicated and it's sort of beyond what this demo is about. But as you dig into clustering algorithms, these metrics are pretty standard. And finally, the number of points metric tells us how many penguins are in each cluster. And the last row tells us how many penguins there are in the total dataset. Ideally, a really good cluster would have the penguins evenly distributed, but that's not totally necessary either. If you have 50 emperor penguins and 10 crested penguins, you don't have to get too complicated to group them. Now, at the end of the day, we can look at these values and we can say that our model did a pretty good job in distributing our penguins into groups. Unfortunately, what this pipeline does a bad job at is telling us what the logical grouping is. I mean, we asked for a grouping because we didn't really know what the answer was, but we also really didn't get an answer as to what the grouping ended up being. But not so fast. Let's go look at the dataset generated by the Assign Data to Clusters module. In this dataset, we can see each of the 103 penguins that were fed into this module. We also see 4 columns of information that were attached to the dataset at the end. The important column of information is the assignments. In that column, we can see that each penguin has been assigned to cluster 0, 1, or 2. Now, it's still not overly obvious, but you can look at the data for each cluster and discern from there what characteristics of each penguin warranted that penguin being in one cluster versus another. Now, that'd be pretty tedious, but it could be done. Regardless, we've walked through a pipeline that can cluster data into an arbitrary number of logical groups. In this demo, we're going to create an inference pipeline in Azure Machine Learning Studio. To do that, we're going to use our existing regression pipeline to perform some transformation on a new dataset, and then use our already trained model to inference, meaning predict, the price for some new cars. First, we need to navigate to the Azure Machine Learning Studio in our browser. Now what we want to do is create an inference pipeline for our existing regression pipeline. So to do that, we need to access our regression pipeline. So let's do that by clicking on the Designer option in the menu. Now let's go ahead and click on our regression pipeline. For me, that's SB Test Pipeline Regression. Good. So we are once again presented with our regression pipeline. Just a simple recap, remember that this pipeline takes a sample dataset about cars, cleans up that dataset using some transformers, and then trains a model using a simple linear regression and 70% of that dataset. And then it validates the result using the scoring module and an evaluation module. Now what we want to do next is be able to feed in new datasets against the model that we just trained. To do that, we need to create an inference pipeline. So let's go ahead and get that ball rolling. To create an inference pipeline, we need to click on the Create Inference Pipeline button at the top of the screen. In the drop-down, there are a couple of options. Now for us, we want to be able to test datasets on a sort of ad hoc basis. So we're going to choose the Real-Time Inference Pipeline option. Perfect. So what we've got now is a whole new pipeline, and it's worth noting that this is pretty much the same pipeline as we already had, but with a few differences. First, you'll notice at the top of the canvas that there's a Web Service Input module. Now that's been placed right beside the Dataset module, and they both feed into the next module. What that means is that this pipeline can now be triggered by a dataset sent in via Web Service Endpoint. Well, that's pretty fancy, and we'll get to that later. Next, you'll see our usual Select Columns and Dataset Transformation module to remove the column we don't want. And there are two Apply Transformation modules, and this is just a different way to represent our removal of rows with missing data and our normalization steps. Next up, we have the Score Model module. This takes our trained model and applies it to whatever dataset is provided. And finally, the pipeline outputs the results to two modules. One is the usual evaluation module so that we can explore the results later on, and the other is a web service output module so that we can return information to the consumer. Now that all sounds pretty wild, right? Well, I'm going to make a few modifications to this pipeline to make our lives a little bit easier. First, I'm going to rename the pipeline so that it matches my existing pipeline a little bit closer. I'm going to call the pipeline SB Test Pipeline Regression Inference, and I can do that by using a little cog icon beside the pipeline name and then typing the name into the configuration panel. I'm also confirming the compute target is configured properly. Next, I'm going to remove the original sample dataset. That dataset was used to train a model, but isn't needed when it comes to actually running in the future. So let's just select that module and click the Delete icon in the toolbar. Now what I do want is the ability to run this manually and be able to provide data on the fly. So to do that, I want to add a module for manual data entry. So let's search for Enter Data Manually asset and drag it into the canvas where the original dataset was, and let's connect it to the Select Columns and Dataset module. You'll notice that there's a little warning symbol on the module, and that's because the module expects some data. So let's give it some. Now I'm going to copy and paste some CSV data into this display, but don't worry, I'll include it in the doobly-doo so that you can use the same thing. Good. Now it's actually important to note that in the dataset that I've just provided, there's no price column. And that makes sense, right? Our goal is to predict price. And once we put this out into the wild, there would be no price information anymore. So that means that we need to make a modification to some of our pipeline. So let's click on the Select Columns and Dataset module. And let's edit the columns for this module. Now, since price is not a column of information that we're going to provide, we need to remove it from the list. So let's find it in the list and remove it and click Save. Perfect. Now the next thing that we want to do is remove the Evaluate Model module. When this pipeline is run by consumers, they'll have no real access or need for this module. So it's not really needed in this pipeline then, is it? So let's select it and delete it using the delete button in the toolbar. Good. Now we come to the fun part. What we want to do next is actually add some Python to the pipeline. What we want our Python script to do is augment the output of the pipeline to only return the predicted price data. If you remember, the score model module actually outputs the whole dataset with a new column of information that represents the prediction. Well, the consumer doesn't need their whole dataset back. They just need the price. So we're going to add some Python that will do that for us. So let's get to it. Now we want to put the Python script right before the output. So that means we've got to delete the existing connection between the score model module and the web service output module. So let's do that by clicking on the line and selecting the delete button in the toolbar. Now let's move the web service output module downwards to make room. And now let's search for the execute Python script module and drag it between those two modules. Good. Now let's connect the output of the score model module to the leftmost input of the Python module. And then let's connect the left output of the Python module to the input of the web service output module. Excellent. Now we have a module that's capable of executing Python against the data coming out of our scoring module. But we want to set what that Python is. So let's click on the Python module to make sure it's selected and view its configuration panel. Now let's click on the Edit Code button so that we can see the code a little bit better. Good. Now I'm going to paste some code in here and then we can talk about what it does. But once again, don't worry, I'll provide that code in the doobly-doo so that you can use it later. So what this code is doing is fairly straightforward. There's a main function that gets executed when the module is run, and that function takes up to 2 datasets. In our case, we only populated one dataset, the leftmost, and so we only concern ourselves with data frame 1. If we connected to the middle input of the module, we'd have to use data frame 2. Anyway, we create a variable called scored results, and we place the values from the scored labels column into that variable. Now remember that the scored labels column is our predicted price. But since that label's not helpful to consumers of the pipeline, we also run a bit of code that renames the column to predicted price. Then the variable is returned from the function. Now it's worth noting that the data type is still a dataset, it's just only got a single column in it. So let's go ahead and save this. Perfect. So now we have a pipeline that takes in data from a web service input or manually, does the usual cleansing, though now without the price column, and then applies our model. The output of the model run is then reduced to a single column by our Python script and then sent out to a web service. So let's try it. Let's click on the Submit button at the top of the page. And let's put this into a new experiment just like we've done before. Okay, now let's let this run. Now it may take a few minutes, so I'll fast forward so that you don't have to wait. Perfect. Our pipeline executed. So let's go look at the results. We can do that by looking at the output of the Python module. So let's click on it and go over to the Outputs tab and view the dataset it created. Notice that there are 2 output datasets. Remember that there were 2 input datasets, so you can flow those through. So in our case, we manipulated the first dataset, so we want to look at the result dataset versus the result dataset 2. So let's take a look at it. Awesome, so now we see a dataset that only has a price column. It only has 3 values, one for each row that we sent in manually, and it only has one column, and that column has been renamed to represent that it's a predicted price. Fantastic work! In this demo, we're going to examine the web service inputs and outputs for a real-time inference pipeline in Azure Machine Learning Studio. We'll work to understand what these modules are for, how they're configured, and how they'll ultimately be used. Then we'll configure the modules in preparation to deploy our pipeline. Alright, so first, as usual, we need to access the ML Studio using our browser. Perfect. Now what we want to do here is play around with a couple of modules that will allow our pipeline to be accessible as a web service. So naturally that means that we need to go and edit our pipeline. So let's go ahead and click on the Designer option in the left-hand menu. The Designer screen obviously shows us all the pipelines that we have in the system. In our last demo, we created a new inference pipeline that interacts with our trained model from our regression pipeline. I named that new pipeline SPTest Pipeline Regression Inference. That's the pipeline we want to be able to interact with from a web service perspective. So let's go ahead and click on that pipeline. Excellent. Now we can see our pipeline. Let's do a quick recap of what's going on here and then what we want to do from there. First, we have a dataset input. We actually have two mechanisms for input. The first is a manual data entry module and the other is a web service input. Both of these modules offer the ability to trigger this pipeline with a set of data, and we'll get back to the web service input in just a second. Once we have a dataset, we transform the dataset in a few ways. The first thing we do is remove unwanted columns from the dataset. Actually, more appropriately, we choose specific columns of data that we want. Now, technically, we don't really need this transformation layer anymore, but leaving it here means that users could theoretically pass in datasets with other columns in it, and we'll just ignore that data. The next transformer removes any rows of data that have empty values. And the last transformer normalizes certain values so that they're all using the same scale. When we trained the model, this reduced bias that the model may come up with for certain columns of data. But now it also means that using the model means that the data has to be at that same scale. Once the dataset is cleaned up, we pass it to the model scoring module. This module applies the trained model to the provided dataset, and this is the point in which the prediction for the price of cars is made against the dataset given by the user. Once the prediction is made, meaning once the model is run against a dataset, our Python script is run against the result dataset so that we only output the predicted price value. And that's when we run up against the web service output module. This is the point where the result dataset would be output to the user. And that brings us to the question, what do we do from here? Well, now that we have a model, what we want is for users to access that model and submit their own datasets for prediction. Specifically, a user may have a new car or even a used car, depending on the nature of the model, of course, and they might want to use this service to tell them what the price of that car should be. They'll need to provide an input, and then they'll expect an output, and so that's what we want to do for them. Ultimately, the way users will interact with a pipeline is to deploy it with an endpoint. But what we want to do here is configure how the user will actually interact with this specific pipeline, and that's where the two web service modules come in. First, let's talk about the web service input module. This input module helps tell the deployment service that this pipeline is to be made accessible as a web service. It's that simple. Now let's click on the input module. Now you'll see in the configuration panel that you're shown a single field. The name field is read-only and is used to identify the name of the object to use when submitting data to this pipeline. But what does that mean? Well, when a consumer accesses this pipeline from an endpoint, they'll want to submit a dataset to this pipeline. The question is, how would we do that? Obviously, we can't put all the data into the query string of a URL, and clearly we're going to have to post that data to the body of some request. But how will the endpoint know that some information belongs to this dataset and some other information belongs to another dataset? What if I had two web service inputs? How would I differentiate the two? Well, that's where this name comes in. When data is submitted to the pipeline, the information is expected to be provided in a body variable that is named Web Service Input 0. Just like this. If there was another web service input in the pipeline, it would be named Web Service Input 1. And so the user could pass both bits of information into the body request and differentiate them by name. Now let's talk about the output module. This module tells the deployment that it's expected to package the results of the pipeline run into a response object that the consumer can, consume. It's pretty simple too. In fact, let's click on it. And now you'll see in the configuration panel that you're once again shown a single field, the name field. And it's read-only too. And it's used to identify the name of the object that will be returned to the consumer once the pipeline has finished executing. But what does that mean? Well, when a consumer accesses the pipeline from an endpoint and submits whatever data they want, they'll want to consume the results from the pipeline. So the question is, how do they do that? Clearly there needs to be a response object, but how do I know what to consume in that object? What if there's other data in the response? What if there are multiple outputs? How would I differentiate anything? Well, that's where this name comes in. When data is returned from the endpoint, information is provided in a large response object which contains sub-objects that have the data from however many output modules you have. When data is returned by the pipeline, the information that's associated to this output module is stored in an object named Web Service Output 0, just like this name. Meanwhile, if there was another web service output in this pipeline, it would be named Web Service Output 1, and so the user knows exactly where to get their data from. So with the input and output modules in our pipeline, we're now able to deploy our pipeline as a web service. We've also set it up so that the consumer can know which object to populate when providing input data, as well as which object to look for when they get the response. And now we're ready to create a pipeline deployment. In this demo, we're going to deploy a predictive service using Azure Machine Learning Studio. To do that, we're going to use our existing inference pipeline and use the built-in deployment mechanism to create a new endpoint. Then we'll go take a look at the endpoint details and talk about what this means. Alright, so the first thing we need to do is head over to the ML Studio in our browser. Now what we want to do here is we want to take our existing inference pipeline and deploy it so that it can be accessed from an external source. So the first thing we have to do is access our pipeline. So let's go ahead and click on the Designer option in the left-hand menu. And now let's click on the inference pipeline. Perfect. So now once again we're seeing our pipeline canvas with all the modules that we've been playing with throughout all of these demos. The whole point of this pipeline is to be able to predict what the price of cars should be based on the characteristics or features of cars given as inputs. In other words, if a user says, I've got a classic 1961 Ferrari 250 GT California with 2 doors and a 3-liter engine and 240 horsepower, this pipeline should be able to guess that it's worth $11 million. On the other hand, if a user says, I've got a homemade go-kart with a 600 horsepower pull-start motor and no doors at all, this pipeline should be able to guess that this isn't worth very much at all. Of course, those are extreme examples, and this pipeline probably wouldn't be able to predict those, but it's hopefully the kind of data that you would get. So if we want a user to be able to access our pipeline, the first thing that we need to do is deploy it. So let's go ahead and do that. Now on the top right of the screen is a Deploy button right next to the Submit button. So let's click on that. Deploying a pipeline means creating an endpoint. An endpoint is a URL that can be used to specifically access your pipeline. So the pop-up dialog here is asking us for details about how we want to configure our endpoint. The first question that's asked is whether we want to replace an existing endpoint or create a new one. Well, we've never deployed this pipeline before, so let's choose to deploy a new one. The next question is what we want to name our endpoint. Now this can be anything you want, really, just as long as it's less than 32 characters long. So I'm going to name mine SB Test Pipeline Regression EP. Next is the description, and this can be useful for Swagger information, and I would generally recommend setting this value, but in this case I'm going to leave it blank. And lastly, we have the compute type selection. Now, because this is an inference pipeline, we can technically use a Kubernetes service to run our endpoint. If we leave that selection, we're asked to choose a Kubernetes cluster to use. But in my case, I don't have a Kubernetes cluster, so instead I'm going to select the Azure Container Instance option. Good. Now our endpoint is ready to be created. So let's go ahead and click Deploy at the bottom. Now the endpoint creation process may take a moment, so I'm going to fast forward a bit here. Good. Now at this point, our endpoint theoretically exists, so let's go check it out. Now to do that, we need to head over to the Endpoints option in the left-hand menu. Awesome. This particular screen shows us a list of all the endpoints that we've created in the system. There's actually a few ways to create endpoints. In fact, one thing you can do is train a model through some automated ML. Then once Azure has determined the best model for making predictions, you can then deploy that model from there. That would result in an endpoint configured for you without having to go through the pipeline steps necessarily. This can be a simple thing to do, but it can also skip some much needed steps like all the data transformation we did. Anyway, we're interested in the pipeline that we just deployed, so let's go ahead and click on that endpoint that we just made. Great, so here's our endpoint. The endpoint details page shows us a bunch of information about our endpoint. We can see its ID, its deployment state, which is healthy, the type of compute it's using, who made it, how much resources it uses, which pipeline it's linked to, and even which specific model run it's related to. Perfect. But let's remember that the goal of our deployment is so that users can interact with our pipeline and make price predictions on the car datasets that they provide. So with this endpoint created, users can now access our pipeline. Well, almost. There's actually two specific bits of information that they need to do that. And some of that information is already on the main details tab, but all of it is on the consume tab. So let's click on that tab. Good. Now, in order for a user or an application or really any consumer to interact with our pipeline, they need the URL of this endpoint. And we can see that right at the top of this tab. The REST endpoint field contains a URL for our pipeline. If a user has that URL, it will take them directly to our pipeline input. But just having the URL isn't enough. Our endpoint is secured through a key mechanism. So not only does the user need the URL, but they also need one of the keys. But it doesn't matter which one. It's worth noting that you can actually regenerate these keys, and in fact that's a good idea to do from time to time. But it's also worth noting that if you regenerate these keys, consumers that are using older keys may not be able to access this endpoint anymore. And really, that's sort of the point, isn't it? Anyway, perfect. At this point, we've successfully created an endpoint for our pipeline. Users that have the endpoint URL and one of the keys will now be able to interact with that pipeline, submit specifications about a car, and then receive back predictions about the likely price of the car. Now we're cooking. In this demo, we're going to access our deploy pipeline to get a predicted price for a particular car. To do that, we're going to use Postman to submit a dataset to our deployed endpoint and read back a predicted price. Okay, so one last time, the first thing we need to do is access the Azure ML Studio using our browser. So what we want to do here is actually access our pipeline. It's actually worth noting that we could do all of this work in lots of different tools. That includes the Notebooks feature in Azure ML Studio, actual application code, or really any API interaction tool. In our case, we're going to use Postman. But regardless of which tool you prefer to use, you'll need to get certain bits of information before you're allowed to interact with our pipeline. So let's go and get those bits of information, shall we? So let's go ahead and click on the Endpoints option in the left-hand menu. Perfect. So here we're presented with a list of all of our endpoints. In my case, I only have one endpoint, so I'm going to go ahead and click on it. This is the endpoint we created to interact with our car price prediction model. Now, when a consumer wants to talk to an endpoint, they require two bits of information, the URL and a key. Both of these bits of information can be found in the Consume tab, so let's click on that tab. Perfect. Now this screen shows us the REST endpoint and two keys. We're going to need those two bits of information later, so let's go ahead and copy them into Notepad. Perfect. Now what we want to do is actually interact with our pipeline via this endpoint. So to do that, we're going to open up Postman. Now if you don't have Postman, you can get it for free at postman.com. Now Postman provides an interface for interacting with any web endpoint. So what I'm going to do here is bring in a request that I've already prepared. But don't worry, I'll provide that request in the doobly-doo so you can copy it too. First, I'm going to select to import a file using the Import button at the top of the screen. Now I'm going to browse for my file by clicking on the Upload Files button in the middle of the pop-up. Good, it recognizes the file. Now let's click on the Import button at the bottom of the pop-up. Now what we need to do is configure the request with a couple of bits of information that it needs. First, you'll notice that this is a POST request, but it's missing the actual endpoint URL. So let's replace that part that says Your Endpoint with the endpoint URL we copied to Notepad. Good. Now let's click on the Headers tab below the request URL. Notice that there's an authorization header. In that header, the value includes a piece of text called Your Key. So let's replace that value with the key that we copied to Notepad. Good. Now before we do anything else, let's quickly take a look at the body of this request. We can do that by clicking on the Body tab below the request URL. Now the body is where we're defining the input dataset. Now pay special attention to that dataset. Notice how there's an inputs object which contains an array called Web Service Input 0. And notice how that is the exact name of our Web Service Input module from our pipeline. And this is important. If we called that array anything else, it wouldn't work. Meanwhile, inside that array is a single object with fields and values. This object is clearly defining a car. The fields match the dataset that's expected in the input dataset. If it didn't match, there'd likely be issues, or maybe the model wouldn't provide any results at all because the row would be removed entirely. This is a demo after all. Real code would protect against bad input. Alright, now let's go ahead and execute the request and see what happens. We can do that by clicking the Send button in the top right. Excellent! We got a result back. Now let's take a look at that result. Notice that the result object contains a results sub-object that itself contains an object called Web Service Output 0. And notice how that is the exact name of our Web Service Output module from our pipeline. And also notice that the value that's returned is labeled just like the Python script asked it to be. Excellent! So now we have a regression pipeline that trained a model to predict prices for cars. We deployed that model, and then we created a Postman request to access that deployment. In our request, we passed in information about an Alfa Romeo, and our model predicted a price of $16,000. I wonder if Jeremy Clarkson would agree. I mean, that'd be the real litmus test. Who needs this AI business anyways? And that brings us to the end of the demo. Great job! So in this course, we've used the Azure Machine Learning Studio scoring and evaluation metrics to evaluate and test a predictive web service. We did this by exploring using a scoring model component in ML Designer, model evaluator types using an evaluator, running and monitoring a pipeline, analyzing evaluation results and details, visualizing data from the scoring model, investigating and interpreting regression classification and clustering model results, using Python to create an inference pipeline, and adding a web service output, to finally deploying and testing a predictive service. In our next course, we'll identify the uses of anomaly detection and work with the Azure Anomaly Detection Service.